Mhm. Okay, hello everyone. Okay, so before we go to the next part, let me review what we considered the other day, especially the definition of a basis. That is important. So, given a vector space, a basis is a set of vectors, okay, and at this point, a set of vectors in V space. Okay, so you need to consider a set of vectors in V. So in other words, you need to consider a subset of V which satisfies two requirements. One, the set must be linearly independent. And second, it must generate the whole space V. So it generates the whole space. That means if you choose any vector from V space, that V space can be written as a linear combination of the vectors in this basis beta. And since these vectors are linearly independent, that representation of the vectors of the vector with respect to the basis will be unique. So So for any vector in V, if if beta consists of V1 up to Vn, then this V can be written as a linear combination of V1 up to Vn, right? So such numbers x1 up to xn exist because this set generates, okay? This set generates width. So when I choose any consider, when I choose any vector from this V, that vector can be written as a linear combination of the vectors in beta because given this beta, span of a beta equals V. So if you choose any vector from V that can be written, okay, that is a vector in span of a beta. That means a linear combination of the vectors in beta. And since this basis beta is independent, this x1 up to xn, these numbers are unique because these vectors are independent. So that is the definition of a basis. And we considered some examples the other day. Oh, and at that point, if beta consists of n vectors, then at this point, this number, the number of vectors in this beta was called the dimension of beta. So that was the new terminology we considered. So please remember that. So in example one, the zero space is generated by an empty set. Even though, as I said, the zero vector generates zero space, okay, that does not mean zero vector is a basis because this zero vector will be linearly dependent. It cannot be a basis for any space. Okay, so zero is linearly sorry, the empty set is linearly independent. So this empty set is a basis for the zero vector space. And since empty set does not have any vector in it, the dimension of this zero space will be zero. in example 2, in Fn space. What is Fn? That is the collection of all the n tuples of numbers chosen from the field F, right? And that Fn has a basis of E1, E2 up to En. So that will be one basis. So since that basis consists of n vectors, this n, the number of vectors, will be the dimension of the space. And as I said, that is the standard basis, but we have some other bases. For example, if I consider E1, E1 plus E2, E1 plus E2 plus E3, that will define a basis for R3 space. So the dimension of R3 space will be 3. Also, you can count the number of vectors in the standard basis for R3 space. But anyway, you get 3 vectors. In example 3, we considered the space of m by n matrix. And in that matrix, we consider e to the ij to, okay, that is the matrix which has non-zero value 1 in the ith row and jth column. So for example, e to the 1 1 has this 1 in the first row, first column. E to the 1 2 has this 1 in the first row, second column, and so on. Then this e to the ij, the collection of e to the ij will be a basis for this space. So how many matrices do I have? M times n. So that m times n will be the dimension of this space. So for example, if I consider M sub 2 by 2, the collection of 2 by 2 matrices, that any matrix with those 4 numbers can be written as a linear combination of these 4 matrices. But that is not the only basis. For example, if you consider 1 0 0 1, 1 0 0 negative 1, and 0 1 1 0, and 0 1 negative 1 0 is another basis. So these are some examples of a basis. In Pn space, the monomials will define a basis, but you can consider some other combination of those functions to define a basis. One important observation you need to consider is that the number of vectors in this basis will be n plus 1, not n. So you need to include 1, the constant function, or mathematically, that is the 0th power of x function. So you have this m plus 1 vectors in a basis. If you consider some other bases, they also have m plus 1 vectors. If you have less than less than n plus 1 vectors, then the set will be, that won't be a spanning set. And we consider this. Okay, so as I said, one usage and very important usage of a basis is that given this vector, given any vector space, and if I consider any basis, then for any vector v in this space, we can find some numbers a1, a2 up to an, such that this v can be described as a linear combination of those vectors in this beta, using those a1 up to an as the weights. And theorem 1.8 says if these vectors in beta define a basis so that if they are linearly independent, then these numbers a1 up to an will be unique. And this is important property. Okay. And this 1.8 holds for any vector space V. So in P2 space, the polynomials of degree 2 or less in P2, if I consider say T 1 plus, so we were okay X. So if I consider any polynomial, say 1 plus 2x plus 3x squared, if I choose the standard basis of 1 x squared, then that px can be written as 1 times 1 plus 2 times x plus 3 times x squared. So 1, 2, 3 are a1, a2, a3. If I consider, say, different bases, say some basis C with, say, 1 plus x, and 1 plus x squared, then the same polynomial P can be written as 3 times 1 plus x squared plus minus 1 times 1 plus x and minus 1 times 1 plus this. So if I change the basis, if I consider different bases, the numbers A1, A2, A3 will be different. Oops, just right. No. I made a mistake. Sorry about that. I made a mistake with this calculation, so it should be minus 2, just 3x squared, 3x. Oops, it is correct. Hmm. So 3x minus 1 is 2x, 3 minus 1, 2 minus 1. Yeah, I think it is correct. So, given this vector space V and some basis, we can always write down any polynomial or any vector in the space with respect to the vectors in a basis. And this a1, a2 up to an, these coefficients will be unique. Okay, but if we change a basis, if we consider different basis, the numbers will be changed. So that was 1.8. In 1.9, okay, if a vector space V is generated by a finite set, then so S is a generating set as a generate. So this part says the span of S equals V. In that case, some subset will be a basis. Now, why is it so? Because this S may not be independent, right? So I'm using this effect. If S, which consists of k vectors, if that S is linearly dependent, then one of the vectors can be written as a linear combination of the others, which we already observed. So in that case, even when I remove that element from the set, they generate the same space. So if S generates V, and if S is not independent, yeah, if S is independent, then S will be a basis. But if S is linearly dependent, which means there is some kind of redundancy. Okay, so we need to eliminate this redundancy. Okay, and I don't need that redundancy because even without this, use of I, the space will generate the same space as before. So if S generates the whole space, then you need to eliminate any redundancy if it exists until when you have a set of linearly independent vectors. Okay? So now if you have a linearly independent spanning set, then that will be a basis. If you remove one more vector, then the remaining vectors will not generate the whole space. Because as I said, as we proved, so given u1 up to un, if I know that this set is linearly independent, then so v1 up to vn is independent, then the union of v1 up to vn and another vector v is independent if and only if v is not in the span of these n vectors. Or you may say the set is linearly dependent if and only if v is included in the span of v1 up to vn, right? So these two statements are equivalent, right? So anyway, since we have this, if this v was chosen outside of this space generated by n vectors, then this collection, the union of n plus 1 vectors, will be still independent. But if that vector was chosen from the space generated by these n vectors, then this union will be definitely linearly dependent. So we had that theorem. So using that theorem, if I have linearly dependent but generating set S, then I can safely remove any redundancy from this S. So that if you have the minimum, okay, the smallest size generating set, that will be your basis. In other words, a basis is a minimal generating set. So that was the theorem 1.9, and in 1.10 in replacement theorem. So if a vector space V is given, and if that is generated by some set, say G, then some elements in G can be replaced by linearly independent vectors. Okay, so the replacement theorem says if G generates V space and if G contains exactly n vectors, then when I replace some vectors in G with linearly independent vectors with the same number of linearly independent vectors, then we can replace some elements with linearly independent vectors, meaning even after the replacement, this set will still generate the whole space. So that is the meaning of the replacement theorem. So one more time. So if span of G equals the whole space, then then we can define, we can replace some vectors in G with linearly independent vectors. And let's say G prime is this new resulting newly obtained set. Then we can replace this span of this newly obtained set G prime is still V. So that is the claim of the replacement theorem. And please, and let's consider the corollary. So suppose that V is a vector space having a finite basis, then all bases are finite and every basis has the same number of vectors. And I already explained this. Okay. But we can use this, right? I mean, previously, as I said, so first the proof regarding the claim that the number of bases, the numbers of okay, so all bases, every basis contains the same number of vectors. For that claim, one proof will be this. So suppose that we have two bases, okay, say beta and gamma. Now, beta is a basis, which means it is independent. And gamma is a set of vectors which spans the whole space. Then, then from the previous theorem, if you have, and if the number of vectors in beta is m, and suppose that the number of vectors in gamma is n. Okay, then for so here beta consists of u1 up to un, and gamma consists of v1 up to so beta consists of u1 up to um, and gamma consists of v1 up to vn. In that situation, Since V, this gamma spans V, U1 can be written as a linear combination of V1 up to Vn. So we have some numbers, say A sub 1, 1, V1 up to A sub N1 Vn, and U2 can be written as A sub 2, 1 V1 up A sub 1, 2 V1 up to A sub N2 Vn, and U sub M will be A sub 1M V1 up to A sub Mn Vn, right? So we have such numbers. So if I define a matrix with those numbers, then this is the matrix with these Mn numbers, and I know that beta is a basis, meaning U1 up to Un must be linearly independent. Okay. So these columns must be independent, meaning N must be greater than or equal to M. Otherwise, we have a problem. The matrix will have, so claim here, you need to think is this claim. Since beta is linearly independent, we can show that the columns of A are linearly they are all vectors in Rn. So these columns will be linearly independent in Rn space, so that the number of columns, in this case M, must be smaller or equal to, or this M cannot be larger than N. So that this is important. Because if M is greater than N, the columns will be dependent. And this is what I want to claim here. So please think about the reason. You should be able to prove this. Okay. So I will go back to this claim later. Okay. But you need to think. So I want to claim that statement. Okay. So that N cannot be greater than M. And then if I switch the role of beta and gamma, now if we use the fact that beta spans the V space and gamma is linearly independent, then we can show that the opposite direction of the inequality. So in that case, N will be less than or equal to M. So by combining these two, we can show that m and n are the same. So anyway, based on what you learned so far, you should be able to prove this claim, or at least you can check this claim. Then the benefit of this claim is that I'm just transforming the problem from general vectors in some general vector space to the numbers. Okay, I am considering certain matrix A with numbers. Previously, beta, gamma are some vectors in vector space V. This V can be a space of polynomials or space of matrices, whatever, right? But I'm just replacing the viewpoint with the numbers. And then if I have that matrix A, then I can claim this one. You can check. And if that is true, the other direction can be easily obtained because I can just switch the roles of these two bases. Then I can show that m and n must be the same so that every basis has the same number of vectors. So this is one way to prove this claim. In our textbook, we are using different approach. So here is the second approach, second proof. So suppose that beta is a finite basis for V with exactly n vectors, and gamma is another basis. Okay. Now, if if gamma contains more than n vectors, then we can select. Okay, so if gamma contains more than n vectors, then by the previous theorem, this gamma is a basis. Okay, gamma is a basis. So gamma is another basis. So between these two, before if we need to claim, we need to mention that the span of gamma will be the V space. So gamma generates V space, right? Then we can select a subset of gamma, okay, containing exactly n plus 1 vectors. And since S is linearly independent and beta generates gamma, the previous theorem implies that, is that correct? So this subset with n plus 1 vectors, okay? We have n plus 1 vectors in this subset, okay? But beta generates V, right? And beta is a basis, meaning, I'm sorry, this S is linearly independent and beta generates V. So n plus 1 must be less than or equal to n, which is a contradiction. So if the gamma contains m elements, then m cannot be less than n. So this one is, okay, corresponding to this portion up to this one, okay, but I'm using some matrices. I just use the fact that each vector can be represented in terms of another basis. So that's what I used in my proof. In the textbook, the corollary is using the replacement theorem to derive this inequality. And then reversing the roles of these two bases, we get the other direction of the inequality. And then you can combine these two inequalities to show that m and n are equal. So we can use the replacement theorem as in the textbook, or you can use my approach. Okay, but in that case, you need to make sure that this claim is correct. Then you can use my proof. And in either way, the point is that the number of bases, the number of vectors in a basis will be the same. And this number is called the dimension. And as I said, we can consider the zero space, the Fn space, the space of matrices, and Pn. You need to be careful with the Pn because for Pn, the dimension is n plus 1, not n. So please be careful with this Pn space. And one important, not important, but it is, you should be careful. So when I consider the vector space of complex numbers, the vector, okay, the vector space of yeah, the vector space of complex numbers, this is my V. If the scalar field is C, then any number in this V can be written as, so any complex number, say 3 plus 4i in V space, can be written as 3 plus 4, that is 3 plus 4i times 1. And this 3 plus 4i is a number in this scalar field C. So if the scalar field is the set of complex numbers, then any value in this V space can be written as that number multiple of 1. So this 1 can be your basis. But for the same space, if you restrict your scalar field to the real numbers, then 3 plus 4i cannot be written as 3 plus 4i times 1 in this case, because this 3 plus 4i is not in the real scalar field. Instead, you need to use two different vectors in a basis, say something like 3 times 1 plus 4 times I. Then this 3 and 4 are real numbers. So this 1 and I can define a basis. Of course, you can define 3 and I as another basis, and you can express a 3 plus a 4i by 1 times a 3 plus 4 times I. Then 3 and I will generate an arbitrary complex number, right? So when you consider the dimension, or when you consider the vector space, you need to be careful. You need to be careful with the scalar field. So depending on the scalar field, okay, the dimension may be changed, may be different. So the dimension of this space V, this vector space of complex numbers, the dimension will be 1 if the scalar field is the complex numbers, but dimension will be 2 if the scalar field is the set of real numbers. And Oh, and the yeah, this is trivial. So the theorem says if V is generated by exactly n vectors, in other words, okay, so this replacement theorem, okay, says that if V is a finite dimensional vector space, then 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 no linearly independent subset of V can contain more than this number of vectors. Now in example 3, this PF is, as I said, this is an infinite dimensional space because no finite set generates this PF. We need infinitely many vectors. So this is a little bit different. This PF is different. And in our class, we will usually consider finite dimensional vector spaces. So we are not going to, I mean, this PF is given, that PF is considered in our textbook just to show some exceptional situation which the finite dimensional vector space usually do not hold. So, but in general, in our linear algebra class, we will play with matrices, and most theorems consider only finite dimensional vector spaces. The next corollary is the following. Suppose that we have a finite dimensional vector space V. So this V is an n-dimensional space. Then any finite generating set, any generating set for V contains at least n vectors. Okay? At least n vectors. So if you have less than n vectors, that set cannot contain the whole space. That's the first part. And the second part is that among those generating sets, a basis has the smallest number of vectors. Actually, it has exactly n. So so let us consider the proof first, and then let me go back to the theorem. So let us consider that statement. Any finite generating set contains at least n vectors, and a generating set that contains exactly n vectors will be a basis. Let beta be a basis for this V space. Okay? And let G be a finite generating set for V. Then, if G generates V, so span of G will be V space. Then the previous theorem told you that there will be some subset of G which is a basis for V space. And at that point, I told you that I need to remove any redundancy from G, right? That's what I told you. Anyway, the corollary 1 implies that H contains exactly n vectors, okay? Because the number of vectors in a basis will be the same for all bases. What corollary 1 implied. So if so so if if the dimension of the space is n, then and if H is the basis, then H contains exactly n vectors. Now, since a subset of G contains n vectors, okay, this subset is a basis, right, with n vectors, then G includes this. G contains this subset. So the number of vectors in G must be at least n. So G must have at least n vectors. Now, if G contains exactly n vectors, okay, then we must have this subset H must be the same as G, because H is a subset of G which has exactly n vectors. Now, if I know that G contains exactly n vectors, then H and G must be the same, so G will be a basis for V space. Okay. Now the point is this. Okay, and I wrote down. I put the basis, the proof for statement the B and C there, so you can read them. Those are trivial. But the point is this. In this corollary, what is known? V is a vector space of dimension n. So this is known fact. So if I know that dimension of the vector space I consider is given, if the vector space is n-dimensional, then then what is the second part of statement A? A generating set with exactly n vectors will be a basis. Please remember, we required two conditions for a set to be a basis. If the span of the given set is the whole space, and if G is linearly independent, then this set G will be a basis of V space, right? So I need to check the two things, two conditions. Now in part A, what is checked here? I just checked that this G generates the space V. But I didn't check the independency of the set G. Okay? But it will be a basis. Why? Because I already know that the dimension of V is n. So if I know that the dimension of V is n, and if I found somehow a generating set, and if the generating set contains exactly n vectors, then you do not have to check the independency of those vectors. Those vectors will be always independent. Okay? So here is the fact. So part A says dimension of V is n, okay, and beta with beta with n vectors generates this V space. Then the statement A says we can derive two things, two facts. First, this beta will be independent. And second, so since this beta generates V space and it is linearly independent, so beta will be a basis. So that is the claim of part A. Okay? So that is the part A. Now, what is the statement B? If you have a set which is linearly independent, and if the number of vectors in that set is n, then it will be a basis. So as I said, if the dimension of V is n and beta with n vectors is independent, then the claim is, first of all, the span of G will be the whole space. So that this G, I'm sorry, span of beta will be V, so that this beta will be a basis. So that is the meaning of this corollary. Okay, so this is important. So in A, in A, so what is known? I know that the dimension of this V space is N. In that case, if I know that this set generates the whole space, if you have these two facts, then I can derive two things. This set will be independent, first of all. That's the first claim. So that the set will be a basis. So this independency of the vectors can be replaced by this condition. So if I know that the dimension of the space is n, and if I can find n vectors which generates the whole space, then you don't have to check the independency. The set will be always linearly independent, so that it will become a basis. And we observed that so if a set of n vectors generates n, then any set, I'm sorry, if if the dimension is n, and please note, if the dimension is n, we can always show this one. If S prime generates V, then the number of vectors in S prime will be greater than or equal to n, right? So, as I said, a basis is a minimal generating set. So in other words, it is a generating set with the minimum number of vectors. So it is a generating set with the minimum number of vectors. Okay. And corollary B says, if your dimension of V is n, so if I know this fact, okay, and if the set of n vectors is independent, then the set will be always generating the whole space, so that this beta is a basis. And also, if beta prime is independent in V, then the number of vectors in beta prime cannot be greater than n. Okay, so previously the number of vectors of a generating set was greater than or equal to n, and the number of linearly independent vectors will be less than or equal to the dimension of the space. So in this sense, the a basis is a maximal independent set, meaning that is an independent set. Okay, it is a set of independent vectors. Okay, it is a set of independent vectors with the largest number, with the maximum number. If you have more than n vectors, then the set will be linearly dependent. Okay, so if a set contains exactly m vectors, and if m is less than n, then the set cannot generate V space. And in a similar way, if a set contains exactly, let me just use m vectors, and if m is strictly greater than n, then the set cannot be linearly independent. And vice. Okay, so that is the claim we can derive from this theorem. Okay, and this is a trivial, so you can read this to see. So let us consider some example. So here, x squared plus 3x minus 2, 2x squared plus 5x minus 3, and minus x squared plus 4x plus 4. It is the basis for P2 space. Now, how can I prove this? So there are several ways. The proof number one, you can prove that the set generates the P2 space and it is linearly independent. Proof number two, since I know that the dimension of P2 is 3, you can just show, and I have 3 vectors. So you can just show, so here number one, you can show the spanning part and the independent part. Okay, I mean, you can just use the definition of the basis, or by using the previous theorem, using the fact that the dimension of P2 space is 3, I know this. So, and I have 3 vectors. So what you can do is you can just show one of these two. Okay, you can just show that these 3 vectors will generate the whole space. So if you want to show that these vectors generate the whole space, then in that case, you need to show that for any polynomial in P2 space, there exist some numbers C naught, C1, C2 such that C naught times x squared plus 3x minus 2 plus C1 times 2x squared plus 5x minus 3 plus C2 times negative x squared minus 4x plus 4 will generate this arbitrary polynomial. So if you can show this existence of these 3 numbers, then, I mean, if you can solve this equation for C naught, C1, C2, then that will prove the first part. I mean, the set generates the whole space, P2 space. So that's what you need to show. If you want to show that this set is linearly independent, you need to show the following. You first set some linear combination of x squared plus the 3x minus 2 plus c1 times 2x squared plus 5x minus 3 plus c2 times negative x squared negative 4x plus 4. You set this to 0 and derive. So you set this implies, so you can just implies that C naught, C1, C2 are all zeros. Between these two, you can choose one of these, okay? Actually, the proof number one need to show both, right? But since I know that this dimension of P2 is 3 and I have only 3 vectors in this collection, I can just choose one of these two. That will be sufficient, right? So to prove that the set generates the whole space, or you can show that the set is linearly independent. So in order to prove that the set generates the whole space, you need to show the existence of these three numbers for any arbitrary polynomial in P2 space. If you want to prove that this set is independent, then you just assume that certain linear combination is 0, and then you need to derive that these three coefficients must be all zeros. So if you show one of these two, not both, okay? If you can show one of these two, then that will prove that the set is a basis. And for these four matrices, in order to prove that this set is a basis, since I know that the dimension of m sub 2 by 2 is 4 and I have 4 vectors, so you can show one of two things. You need to show that these 4 vectors will generate arbitrary 2 by 2 matrix in m sub 2 by 2 matrix, or you show that these 4 matrices are linearly independent. And I have R4 space and I know that its dimension is 4. So in a similar way, you can show that these 4 vectors will generate an arbitrary vector in R4 space, or you can show that they are linearly independent. You can try both, okay? But and then once you prove this, okay, once you prove any of these, you will realize that one will be easier than the other in most cases. Okay, but I don't want to tell you, okay, my choice, because you need to do it yourself. Okay, please, please try to prove these statements. Then you will realize, you will feel, okay, which one is easier. So please try to prove both, okay, the one above in blue and one below in black. So please try to prove both, and then you should have a feeling, okay, probably this one seems to be easier than the other. So you should have such a feeling. Tn is, what is the dimension? Dimension is n plus 1. So I need a generating set with n plus 1 vectors or n plus 1 vectors which is linearly independent. So you can try one of these two approaches, okay, with this example. And if W is a subspace of a certain vector space, okay, and if W is a subspace, then the dimension of the subspace cannot be greater than dimension of V space. Now, because what does the dimension imply? Dimension of W is the maximum. So it is representing the maximum number of linearly independent vectors in the space. So that's the dimension, right? A second. Okay. So dimension is the maximum number of linearly independent vectors. So dimension of a subset W cannot have more independent vectors than V space. So this inequality must be trivial. And if the dimension of W and dimension of V are equal, then these two V and W must be identical, right? Otherwise, if not this one. Here is my V space, and here is my subspace W, and the dimension of V and dimension of W are the same. So that means the number of independent vectors, the maximum number of independent vectors are the same. Then V must be the same as W. Otherwise, if V is different from W, then that means there must be some element Y outside of W, right? Then we have a problem. The dimension of W is, if that dimension is n, then that means we have some basis with n vectors which generates this W. Now if so, this W is the span of W1 up to Wn. If V is different from W, so that if some Y vector exists outside of span of W1 up to Wn, then the union of W1 up to Wn and Y vector will be independent, right? Then, so this will be independent. Then, then we have a problem because the dimension of the original space will be greater than equal to the number of these independent vectors n plus 1, so that it cannot be the same, this dimension cannot be the same as dimension of W. So that is a contradiction, which means there is no such Y vector outside of W, meaning V and W are the same. So we have such proof, so you can read this. Now, let us consider example 18. So W is a set of vectors, set of vector of 5 numbers, and this a1 up to a5 satisfies some condition like this, then this W will be a subspace of F5, right? It is a subspace. Am I correct? Why is it so? A1 up to, okay, so A1 plus A3 plus A5 is 0, and A2 is A4. So that means A1 will be negative A3, negative A5. Okay, so I'm considering a set of vectors A1, A2, A3, A4, A5. And A1 is the same as minus A3 minus A5. And A2 equals A4. And A3 is A3, A4 is A4, and A5 is A5. So this is an arbitrary vector in W space. Now I can rewrite this vector as the sum of three vectors, one vector having only A3 in it, and the second vector having only A4, and the third one with only A5. Then the first one, each entry in the first one is a multiple of A3, and the second vector is a multiple of A4, and the third one is a multiple of A5. So any vector in this W space is a linear combination of these three vectors, meaning these three vectors will generate this W space, right? So this equality shows that any vector in W can be written as a linear combination of these three vectors, so they span the whole space. Now, if the vectors are linearly dependent, then one vector is a linear combination of the other vectors, right? But when I just look at just the third entry of these three vectors, only the first one has 1 while the second and third vectors have zeros. Meaning, if you consider a linear combination of these two vectors, you cannot generate the first one. Now, if I look at the fourth entry, only the second vector, the one in the middle, has a non-zero value 1, while the other two vectors have zeros in the fourth place. So when you consider a linear combination of the first and the third vector, you cannot generate the second one. And when I look at the fifth entry, only the third vector has a non-zero value 1, while the other two have zeros. So that means the third vector cannot be represented as a linear combination of the first two vectors. So no vector can be written as a linear combination of the other two vectors, meaning these three vectors are linearly independent, which means this set is a basis, and the number of vectors in this basis is 3, so W will be three-dimensional space. So please check this example carefully, okay? And we will consider some more examples next time. Okay, thank you for listening and see you next time.